Hi everyone, Dr. Shane here. It has been quite a while since I've done one of these videos. I think since the pandemic. So so hopefully I'm still doing these okay. All right. So this is the pre-lab video for the electrochemistry experiment, which is the last week in Chem 126. And we haven't taught electrochemistry in Chemistry 122 chemical dynamics for quite a while. So I'm not exactly sure how far you will have gotten with this. So I'm just going to review some basic things. What's on the left side of the chalkboard over there the first thing is a picture I took from your book, which is kind of nice. And it shows the three things you should be able to do. I'm going to explain those a little bit more. Calculate equilibrium constants, Gibbs free energy, and cell potentials for standard conditions. That's what the superscript 0 means. And by using K, equilibrium constant, instead of Q, reaction quotient, that indicates a standard condition as well. And then when you have non-standard conditions, where you have to take into account the temperature and non-equilibrium concentration, so not 1 molar, then you have to use what's called the Nernst equation, which is there below. All right, so the pre-lab is going to be based on, that's on the right side over here, so as you can see that, is based on a problem in your ebook. It's in section 17.4. There's an example 17.7 that goes through how to do things and then gives you an example and then asks you to calculate the number of electrons transferred, the reaction quotient, the standard cell potential using the tables in the back of the book, the appendices, which we'll get to a little bit later, and then also then the cell potential under non-standard conditions. And we're going to use that problem as a basis for doing some other ones. Actually, that example mirrors almost perfectly the example for the lab for next week. Okay, first things first. Just some basics. You probably will have done some of this in lecture. So this is the lab itself. So I'm just holding this up here, very high tech. So this is an actual schematic diagram of a galvanic cell, and it's the classic copper-silver one. So what you have on the left side is, it says here, copper anode. So the anode is where oxidation occurs. Okay, oxidation, as you might recall, is the loss of electrons. You might remember the acronym OIL-RIG. Oxidation is a loss of electrons, reduction is a gain, or LEO-GER. Loss of electrons is oxidation, gain of electrons is reduction. So what's happening over here is shown schematically, and you might remember it more just showing an oxidation half reaction. So copper with no charge going to copper plus 2 charge plus 2 electrons. That's oxidation. On the other side, so actually this copper anode is degrading or decreasing in mass over time. On the other side, we have silver. So that's at the cathode, that's reduction. So it's silver plus 1 ions gaining an electron to turn into silver metal. So this cathode, this electrode, is actually getting larger because it's aggregating. There's more surface aggregation or adsorption of silver ions. That's kind of not a great way to explain it. And then the diagram is very good because it shows when you lose the electrons, they flow over to this side where they're gained. Now when we did half reactions, we kind of talked about that. The number of electrons lost has to be equal to the number of electrons gained. That is made, I think, a lot more clear when we talk about electrochemistry. Okay, and then down beneath, I don't know if you've done this in lecture, is a shorthand diagram for an electrochemical cell. What does all this mean? So this, it's very nice because this goes left to right. So the electrons flow from left to right. You put the anode over here, the cathode over here. The double line is the salt bridge, which we're not going to go into that too much. So the salt bridge is there just to keep the charge balance. It basically completes the circuit, if you will. So what you do is you write the reactant, it's copper solid, and the single line is the interface. That is actually the very surface of the solid copper where the reaction actually takes place. So that's the interface between copper and copper plus 2 ions in solution. In this case, a solution of copper nitrate. Nitrate is a spectator ion. And it's a 1 molar solution written up here, so we just put that in parentheses. Salt bridge, then the other side, silver plus 1 molar, says that right there, turns into silver solid. So it's kind of nice to write it out this way. Now, in this case, the number of electrons transferred is going to be 2, because you'll have to, and I'm not going through all of this. So if you have 2 electrons lost, you're going to have 2 electrons gained. This is where you write the half reactions. You multiply one half reaction by some number to make the electrons equal, and you just go from there. All right, so that is just sort of a review of the basic concepts of oxidation reduction and how you write a cell diagram. I think that's what that's called. This is a shorthand version of this, and so I think it's pretty clear. And then when actually you do the Q, so the reaction quotient, let's see, copper 2 plus is going to be the product, so that'll be in the numerator. Silver will be in the, okay, but we're going to get to that later. Then you have to raise it to the power of the coefficients. But that's basically, you've done that with equilibrium. All right, let's step out from behind here and go through this. And like I said, it's been a long time since I've done one of these. Okay, so just to review some basics. You might have done this in lecture, but if you want to go, typically the way you start with basic electrochemistry problems is you go to a table of standard reduction potentials. It's appendix something or other in your book. And then you look up the 2 reactions, and then what you want to do is you add the 2 cell potentials such that you get a positive E0 cell. So what does that mean? So in this case, well, I'll use this example over here. Why don't I just do it now? This is the example from the book. So this is your anode. Aluminum turns into aluminum plus 3. That's oxidation. So you won't find that reaction exactly written in those tables. You'll find the opposite reaction. You'll find aluminum plus 3 going to aluminum. Everything is written as a reduction in those tables. So you would look up that number, flip it, and change the sign from positive to negative or negative to positive, whatever it is. And we're going to give you an example here. The cathode, where the reduction takes place, copper 2 plus turning into copper metal, so it's copper 2 plus 2 electrons going to copper. Be careful when you look up on the table in the back of the book, there's different reactions for copper. Make sure you look up the correct one. And that one you would not change the sign because it's written as a reduction. So I might as well just finish this one off over here, then I'll jump back over there. So in this case, you are losing 3 electrons and then gaining 2. So write out the half reactions for those, and then what would you have to multiply by so that the number of electrons is the same? If you're losing 3, gaining 2, the least common multiple between those is 6. So that's there. And we'll come back to this. So that's a fairly, well, might as well, like I said, I haven't done this in a while. My notes are all over the place. And if you do that for this reaction, you should get a standard. So I haven't considered the concentrations or Q or any of that stuff. And I came up with a positive 2.00 volts, and I only took it out to a couple of decimal. Yeah, sig fig should work out there. I think one of them only goes to 2 decimal places. But you look that up on your own and get that done. All right, now we have to consider non-standard conditions. But before I do that, I want to bounce back over here. These are the pretty typical problems. So you use the tables, you get a cell potential, like I said, you flip one of them, you leave the other one the same, you add them together such that you get a positive voltage. Great. Now you can do a couple of things. From the cell potential, you can calculate an equilibrium constant, and I imagine you're going to be given these equations. So E0 cell equals, I have to look these up, RT over NF, a lot of symbols, natural log of K. So if you want, you'll have to solve this. So if you have an E cell, you want to get the K, you'll have to bring the NF over here, the RT over here, and then take the exponential of each side. I'm not solving all of that, so you should be able to solve back and forth. A couple things. N is the number of electrons. F is the Faraday constant, 96,485, I think. Let's do that from memory. Coulombs per mole of electrons. We're going to try to verify that today. The temperature has to be in Kelvin, and R is the value 8.3145 joules over moles times Kelvin, so that's a little sloppy there. Just to keep in mind, we're not using the 0.08206 from gas laws. Okay, so that enables you to go back and forth here. The equation for delta G and E0 cell is small, I have to write this. So delta G equals minus NF E0 cell. So that's a pretty straightforward calculation. But if you want to get the delta G, or the E, from the delta G, you just have to solve it. And then to go between these two, it's delta G equals minus RT natural log of K. That's just a review. So be able to do those kinds of problems. Those are standard conditions. What is it, 25 degrees Celsius, I can't see me now, and concentrations of 1 molar, 1 atmosphere pressure, all that good stuff. Now the Nernst equation is for non-standard conditions. So in lab, what we're going to do is you'll record the temperature in the lab. That's constant, that'll be constant for this, we already have that one. Well, that's for the check your loading. And we're actually going to calculate experimentally the Faraday constant and the E0 cell. So we're going to use experimental data to get this and this. It's a pretty neat experiment. In fact, I've never seen it before. First things first, I'll come back to that. And that's where we're going to apply the Nernst equation graphically. So we're not just going to put numbers in and solve that. We're going to apply it graphically, and I'll talk about that in a minute. Let's finish this one off though. So Q is kind of like K, right? It's products over reactants, and you have to take into account the balanced equation. So that's going to be the product, and you don't worry about the solid state. So it's just going to be aluminum, and that'll be what, raised to the 2nd power, I think, and then divided by copper raised to the 3rd power after you balance it. And I'm going to let you solve that one. I have it here somewhere. Well, actually, I will do this out. Why not? Just to make sure everybody's on the same page. So it's going to be aluminum plus 3 concentration to the 2nd power over the copper 2 plus concentration to the 3rd power. Put in those numbers, and you get a pretty big number, 1440. That's just straight from the book. And the book doesn't do this. I'm not sure why. It's not that important. But the units here would be inverse molarity. That turns out not to be that important when we solve these problems. Okay, so the basics. So you see a cell diagram. You figure out the number of electrons transferred from anode to cathode. You calculate your Q because these are non-standard conditions. If these were 1 molar, think about this mathematically. If both of those were 1 molar, this whole term would drop out, and you would just have E cell being the standard for the cell. So they're not 1 molar. They're not 1 molar, so we actually have to calculate it. And then I'll let you solve this. So what we do for this problem is we solve it. Put in the E0 cell, RT Kelvin over NF. Now here we're actually using the accepted values. Natural log of Q, just solve that math, and I came up with, and I verified what was in the book, positive 1.97 volts. So really not that much difference than a standard cell potential. So the non-standard is just a mild variation. That's pretty typical. That's pretty typical. All right, so verify all of that. I guess I could show the work for that. Okay, I will, but then I'm going to erase it. So I just want to put in the numbers. There's one point I do want to make. So we're trying to calculate the non-standard cell potential. So we'll put in positive 2.00 volts minus, I want to make a point about units, 8.314 joule 5, I think that's it, joules over mole Kelvin times the temperature, which I think is 298 Kelvin, over 6 and times 96,485 coulombs per vol of electrons. So I just want to point out just the units. Times natural log of messy, I'm sorry. So if you hack out the units, Kelvin cancels, mole cancels, and you're left with joules over coulombs as your unit of this coefficient in front of the natural log term. A joule over a coulomb is the same thing as a volt. It has to be the same thing as a volt. When you take the natural log, units are dropped out when you do this math. I'm not going into that. So this whole term has to have the units of volts so that you can subtract these two. Just be aware about how to do those things. This is a minor correction factor based on the standard cell potential. So those are pretty standard kinds of problems that you can probably see on a test or your final or something like that. All right, so what are we doing in the lab? That's just the pre-lab, just verify all that stuff that I just did. And if you get this far, that's fine. If you want to try doing a dry lab version of what you're actually going to do, then I'm going to give you some data, and you can give it a shot. You can put it on Excel and do it. So what we're doing is we're applying the Nernst equation graphically, but what we're doing is kind of ingenious. We are, yeah, here we go, kind of ingenious. We're going to hold one of those concentrations constant and vary the other one. Now this is not the exact lab one, I'm just going to continue with this example, but it's the same idea. So we're going to take, I'm just going to kind of rewrite this to kind of show you the experimental design. In the dry lab, this is the dry lab calculation. We're going to hold this at 1 molar. Why? Because that's just going to make this term, the numerator there, always be equal to 1. It's just going to be constant. Doesn't matter that we square it, it's just 1. So it's kind of a neat little trick. It's not really a trick. And then what we're going to do, this is not the way the lab is written. We're going to vary the concentration of the other ion. Really messy here, sorry. So that's how the experiment is set up when you read the pre-lab. You're going to hold one at 1 molar, the other one we're going to have at variable. So this will be standard concentration for one of them, non-standard concentration for the other one. And then what you're going to physically do in the lab, if I can find my data, is do a bunch of dilutions. This is, I'm not sure this is exactly how it's done in your lab, but so I took these out to a lot of decimal places. So what you're going to want to do with this data is put it on Excel and then make some graphs and do some calculations. I'm not going to explain everything, but this is a really good last lab to do. So we make a bunch of dilutions. I'm not sure this is exactly the way the lab is set up, but it's fine for this exercise. So we're just going to do a bunch of serial dilutions using pipettes and volumetric flasks. Again, that's all stuff we can do in the lab. So here's a sample where we just dilute, 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 make it pretty dilute. Make sure those are right. 1.2, 0.04, 0.008, 0.0016, those are right. And then we're just going to use the apparatus, the multimeter or multimeter, to measure the voltage. And I think we're going to record actually millivolts, which is fine because they're pretty sensitive. But then just make the conversion to volts. And we're going to measure the cell potential. Now, these are not standard cell potentials because it's not at standard temperature and standard concentration, although that one kind of is standard concentration. That's something to keep in mind. And this is the data. I made up this data. Well, actually, I didn't make it up. I back calculated it. So 2.150 volts, 2.129 volts, 2.109 volts, 2.088 volts, 2.068 volts. Okay, so that's similar to the data you're going to collect. What are you going to do with that? Well, again, it's kind of genius. I'm probably going to need some space. So I'm going to take that space now. So we're going to make a graph. If you know what you're doing, you've read the lab, it's all in the lab itself. So the video is just kind of reiterating what's in the lab. But it may be helpful if you haven't done much of this lecture. So what we're going to do is we're going to rearrange the Nernst equation so that it looks like a line, and it's a pretty mild rearrangement. So we're going to measure those. What we're doing is switching the order of the terms on the right side. This is a very common procedure in science, is you rearrange the terms of the mathematical equation so that you can make a graph and then do slope-intercept analysis. So, well, what are we going to graph? We're going to put that on the y-axis, no calculations necessary. We're going to put the natural log of Q, on the x-axis. What does that mean? All of this will then be the slope, and the standard cell potential should actually be equivalent to the y-intercept. So that's the graph you're going to make. I'm not going to tell you how to do all of that. So what you'll do is you'll leave those, you'll put those on the y-axis. You'll put your natural log of Q on the x-axis, which so it's not just those, you have to actually calculate Q. So that's 1. Okay, so let's just make sure we understand the graphing thing. So make a big graph, get rid of all the dead space, don't have it at 0, 0. So scale it, make it a whole page, print it out, give it a title, axis labels, units, and the data I gave you should be pretty much a dead straight line. Then you can get the slope and the intercept. You can go over what is over the graph. You click on things and put the axis titles, and then the trend line. And you can insert the equation, y equals mx plus b, and the correlation coefficient. We've done that before on the graph, or you can use the function equals sign slope, enter the x and the y data. It doesn't matter which way you do it. But the slope itself, so what are we doing here? That we're getting E cell, that's the purpose of this. And we're also calculating the Faraday constant. Okay? So then what you're doing, and I'm going to go look at the lab just to finish it off. So the slope is not the Faraday constant. So you'll have to figure out the units of the slope, set it equal to this, and solve for the Faraday constant. And I set up the data so you should get a number that makes sense. I mean, the accepted value of the Faraday constant is 96,485. I didn't set it up to be exactly that, and I didn't set up the cell potential to be exactly what the tables give you. Okay, so take a whack at that, see how far you can get, and the last thing I want to do is the calculations and the discussion questions pretty much mirror the dry lab. So I'm just looking at the calculation section. So it says you've done the graphs, okay. Record your experimental slope and intercept in the space below. Okay, fine, that's all that. Use the information from the slope and the intercept to get the Faraday's constant and E0 cell, fine. Number 3 is using the table from your book. Determine the theoretical E0 cell. Okay. So you go to the tables, flip one of them, do all that business, and then you calculate the percent error based on your graphical analysis, and then the tables. I'm sorry, this is quite insulting your intelligence. Then the discussion questions are some of these calculations. Using your results from calculation 2, which is E0 cell, calculate the delta G. Now you have to use the standard cell. You wouldn't use any of those. You'd use the standard cell potential. So calculate delta G, show the units, sig figs, calculate them. So that's discussion question number 1. Discussion question number 2. Calculate the equilibrium constant, and then make some comments. And then there's a couple of other discussion questions. So that should be it. That's kind of a long dry lab there. And again, I haven't done these in a while, so I'm probably a little rusty at this. So that should be good. So make sure you do all that pre-lab, get as far as you can as usual. Listen to whatever your instructor has to say. If you have me for class, just get as far with that as you can for the pre-lab with all the other pre-lab activities, and we'll see you in lab.